Hey, how's it going, guys? In this video, I'll be going over equilibrium of rigid bodies. I'll be covering 3 simple problems, and we'll make a separate video for some more difficult ones. So without further ado, let's get started. So for the first problem, we have a beam with 2 loads. We need to find the reaction at point A, as well as the tension in cable BC. So in order to solve this problem, first I need to draw the free body diagram of the beam. One thing I forgot to mention is that the support at A is a frictionless pin. So that would mean that we would have an X and Y reaction. Finally, we have a short cable BC, and the force will be going through the line of action. So now that we have our free body diagram, we can take the moment about A. We know that the moment is equal to force times distance. We know that D is equal to the perpendicular distance. So for example, we have a 10-pound force on the end of the beam. The green dots represent the line of action of the force. And this would represent the perpendicular distance from the point A to the line of the force. So for force, we have 10 pounds. Times the distance, which is 15 inches. We also need to find the direction of the moment. As a rule of thumb, counterclockwise would be a positive moment, and clockwise would be a negative moment. The way that I determine if it's a positive moment or a negative moment is that I follow the line of action from the point that I'm taking the moment of. So in this case, my 10-pound force is pointing downwards. From point A, I would follow the path going downwards. So it's a counterclockwise moment, which is a positive moment. Now we need to do the same for the other forces. So we have a 20-pound force, and the perpendicular distance from point A to 20, it's 10 inches. Again, this would form a counterclockwise moment, which is a positive. So now we don't have to take the moment of AX and AY. Since point A is in the line of action of AX and AY, the moment of both of these forces is 0. Finally, we have tension BC. And the perpendicular distance from point A to the line of action of tension BC is 5 inches. This time it would be a minus sign. If we follow the path of the line of action from point A, it would be clockwise. And this is equal to 0. After doing some simple math, tension BC is equal to 70 pounds. The sum of the forces in the x direction is equal to 0. Therefore, AX is equal to 0. Finally, I'm going to take the moment about B, and that's just because I want to check the solution afterwards. So the sum of the moments about point B is equal to 0. So we have a 10-pound force. And from point B to the line of action is 20 inches. And again, this would be a counterclockwise moment, which is equal to a positive. Now for the 20-pound force. The perpendicular distance from the 20-pound force to point B is 15 inches. And finally, we would have a negative moment because AY is going in the opposite direction. And the perpendicular distance from AY to point B is 5 inches. So solving for AY, you get 100 pounds. Finally, just to check it, the sum of the forces in the y direction has to equal to 0. So summing up all the forces in the y direction, we get minus 10, minus 20 plus 100, minus 70 has to equal to 0. We can see that the solution checks out. For the second problem, we need to find the reactions at A and B. Here we have a plate with 2 supports, as well as 2 50-pound loads. So first we need to draw the free body diagram of this plate. We start off with our conventional coordinate system. Making some assumptions. At support A, we have a roller which is 45 degrees from the horizontal line. And at support B, we have a frictionless pin. So now drawing the forces. The reaction force at support A is perpendicular to the surface because it's a roller. From geometry, we know that the angle between the vertical line and the reaction force would be equal to our given angle, which is 45 degrees. Finally, at support B, we would have the x and y components of the reaction force because it's a frictionless pin. Now, taking the moment about B, we can find the reaction at A. So sum of the moments about B is equal to, in this case, the vertical force, which is 50 pounds, and the perpendicular distance between B and the line of action of the force, which is 35 inches. And again, a counterclockwise moment is positive, and a clockwise moment is negative. So this would result in a positive moment due to the counterclockwise rotation. Next, for the horizontal 50-pound force, the perpendicular distance is 20 inches, and this would also result in a positive moment. Finally, we have the reaction force R of A, which is coming in at a 45 degrees angle. We will now have to break up the reaction force into its x and y components. Since point B is on the line of action of Ra of x, the moment of Ra of x is equal to 0. So we just need to take the moment of Ra of y. Using trigonometry, Ra of y is equal to cosine of 45 times the reaction force at A. The perpendicular distance is 40 inches, and the moment in this case is clockwise, so it would result in a negative moment. This is all equal to 0. Simplifying this expression, the reaction force at A is equal to 97.23 pounds. Now, instead of taking the sum of the forces in the x and y direction to solve for B of x and B of y, I'll take the moment about A to solve for B of y. And the reason for that is because this will allow me to check my solution using the sum of the forces in the y direction. So taking the sum of the moments about A, we get the horizontal 50-pound force times the perpendicular distance, which is 20 inches. This would result in a positive moment. Next, the vertical 50-pound force times the perpendicular distance, which is 5 inches. So in this case, it would result in a negative moment because it's going clockwise. Finally, the only moment left is B of y, and that's multiplied by the perpendicular distance, which is 40 inches. This would also result in a positive moment. Solving for B of y, we get minus 18.75 pounds. Now checking the solution, the sum of the forces in the y direction is equal to cosine of 45 times the reaction force at A plus B of y minus 50, which is equal to 0. Substituting in the values, we can see that the solution checks out. Finally, we can solve for B of x using the sum of the forces in the x direction. This is equal to sine of 45 times the reaction force at A plus B of x minus 50 is equal to 0. Substituting in the value for the reaction force and solving for B of x, B of x is equal to minus 18.75 pounds. So there you have it, guys. For the final problem in this video, we need to find the reaction at C. We have a structure with two loads, a fixed support at C, as well as a cable BD. So first I'm going to draw the free body diagram of the structure. Since it's a fixed support at C, we will have an x and y component of the force at C, as well as the moment. Finally, since it's a short cable, we will have the tension along the line of the cable. Now that we have our free body diagram, first I'll break down the x and y components of the tension BD. Let's assume that tension BD is equal to 1500 newtons. We can see that it forms a 3-4-5 right triangle, and we can solve for the x and y components of the tension using its ratio. We know that the x component is equal to the ratio 3/5 times the magnitude of the tension. So that's equal to 900 newtons. We can do the same for the y component. Which is equal to 1200 newtons. Since we have the tension, we can set up the sum of the forces in the x and y direction. The sum of the forces in the x direction is equal to 500 newtons plus 900 newtons plus C of x. Solving for C of x, that's equal to minus 1400 newtons. And the sum of the forces in the y direction is equal to minus 800 newtons minus the y component of the tension BD, which is equal to 1200 newtons, plus C of y, which is equal to 0. So C of y is equal to 2000 newtons. Finally, we can take the moment about C. So the sum of the moment about C is equal to the force 800 newtons times the perpendicular distance of 5 meters, and this would result in a positive moment. Next, we can multiply the 500 newton force times the perpendicular distance of 3 meters, and this results in a negative moment. We also have the y component of the tension, which is equal to 1200 newtons times the perpendicular distance of 5 meters, and this results in a negative moment. Finally, we have the moment about C from the fixed support, and this is all equal to 0. So after solving this equation, the moment about C is equal to 3500 Newton meters. So there you have it, guys.